We'll be telling us about two conferences, one of them, finance properties of block mapping.
Okay, thank you very much, and thank you very much for having me. I'm happy to be here last week of the semester at least. So yeah, for those who knows me, you're going to be very surprised because I'm not talking about arting groups. I'm not going to say the word arting from now on. So I'm going to talk about big mapping class groups. So a subgroup of big mapping class groups, and yeah, how can we use cube complexes to understand some of their fiteness properties? And this is a joint work with Javier Aramayona, Julio Aroca, Skipper and Xiaolei Wu. You will understand why we are so many people in this paper, because first I'm going to do a summary so you are not going to get lost through the talk. And so first I'm going to talk a bit about Higman Thompson's group. Then we're going to talk about a generalization. We'll see why is a generalization of actually symmetric Higman Thompson groups, and that will be block mapping class groups, which are subgroups of mapping class groups of surfaces of genus G with a Cantor set removed. So surface genus G without a Cantor set. And maybe for those who are not into this kind of groups and know something about Thompson groups, we'll say, okay, why Higman Thompson groups and block mapping class groups? Actually, the story is kind of funny because there is a bridge between these two classes of groups. And for a while, for last 10 years, people were doing similar things with different techniques and having the same results. Something like more algebraic and something more topological. And it's very interesting. So then we're going to study the sorry for my English, finite properties of these groups. Because the thing is that families that are related to Thompson's groups normally are F infinity. I suppose everybody knows who means B of type Fn. I can explain it. Yes? No? Say it, no problem. So a group G is of type Fn if there exists a CW complex with contractible universal cover, such that G is its fundamental group, and and this has a finite N skeleton. And we say that the group has type F infinity if is Fn for every n, right? So normally families related with these groups are F infinity, and what we prove in our article. So our main theorem, poorly stated because I don't have the terminology to state it good for now, is that this block mapping class groups, for now I will just denote it like that, can realize all types of all type of finite properties. So we can find groups of any Fn, but not type Fn+1. It will be clearer in a few minutes. And from this, we will have a corollary that I'm not able to prove yet, but I will. That it's an application and said that the mapping class group of this a surface of genus G without a Cantor set contains a group G of type Fn and not Fn. So basically what I'm saying is that you can use these groups to find examples, all kind of examples regarding finite properties. So this is the summary. Now the talk. Okay, so far so good. So first is about Higman Thompson. So the definition, like classic definition of Higman Thompson groups, is the group of homeomorphisms between covers of the Cantor set. But it's much, or for me, it's funnier to see it like projections between the leaves of trees. So let's explain that. Let's construct a Cantor set. Actually, a D-Cantor set. And at the same time we are constructing the Cantor set, we are going to construct a tree. So we start with one vertex, then we erase this, and these two that are actually covers of the Cantor sets will be like this. Then I do like this again, and 2 and 2, right? And I continue like that. And in that way, I can associate an infinite tree to the Cantor set, right? So if I want to select a cover of the Cantor set, for example, all this and maybe this and this will correspond to this tree in the infinite tree. So when I talk about the Higman Thompson group B, G, I'm talking about bijections between the leaves of trees of the same, for example, here, of the same number of leaves. For example, this will be an element of our group, right? And we consider the elements of the Higman Thompson groups up to an equivalence relation. So, for example, we can expand or add this, we call it a caret. We can add a caret, and if we add it here, then we have also to add one here and to expand it, right? So if we had this before, now we are adding this caret, and this is going the same way, and everything is the same. So we have this equivalence relation. Is it clear? Okay. Okay, so these are basically the elements of a Higman Thompson groups. They're just bijections between the leaves of trees. And okay, here the trees are binary, but if you take the D Cantor set, then the trees are binary. And And yeah, so these are the elements, and these are the equivalence relations between the elements. So you consider the classes of equivalence, and these are the elements of your group. Is that clear? Yes.
So in example, when you add the two pairs,
yeah,
you like were to swap one of them, like, so would it still be in the same equivalence class? No. Like if the two white lines were to swap.
What do you want to do?
Like on the left hand side, there are two parallel.
Here. Here.
No.
On your left.
Yes, there are two parallel white lines that go like
yes.
Yeah. If I swap them.
It's not the same
Not the
for now, because I'm going now to the symmetric Higman Thompson group. So this is the equivalence relation for the Higman Thompson group. But then that Higman introduced in the 70s. But then we have the symmetric Higman Thompson group. And this consists really in changing this equivalence relation, just as you said. So here we have our trees. I think I just do the examples. We have our trees, but we also have labels in our leaves. And these labels, so say G1, G2, G3. Yeah. It's not really important. It's just these labels are in the symmetric group. Okay, in the symmetric group of two elements or the elements in general. So what these labels tell me is that when I change, when I want to add a caret here, I have to apply the permutation that the label is indicating me. So here, if I want to do the same thing, the equivalence relation, so here we have it like that, and like that. So here, if I want to do the equivalence relation and G1 is just 1, 2, then when I add my caret that I was added here, right? I have to do the permutation that the label is indicating. So now I do like this. Is it clear? Yeah. It's just you change the equivalence relations depending on elements that are in the symmetric group. And then the rest is the same. Right. Sorry?
What are the new labels?
Are the same, and then yeah, exactly. Very good question. The labels repeat the same. So this is G1 and G1. Yes. So this is the symmetric Thompson groups. It's just introduction. Okay, and we can't express every element of this group as it follows. So you have the first three. At the end, you have the second tree. Then you have the bijection. So the bijection is an element of the symmetric group that we can call F. My F maybe is not a great. Pick a letter. Sigma. Sigma. You have sigma. And then you have a set of labels. A set of labels in each of the leaves. And this is how I represent an element in the symmetric Thompson group. So at the time when I was in my second PhD, in my second postdoc, I had a friend in Madrid who was Julio Aroca, and he was working a lot in Thompson groups, and we were both very depressed, and I invited him. It was my first Dijon, my first postdoc in Dijon. So I invited him, and we explore the world of braided Thompson groups, which is the same as this, but the bijection is given by a braid instead by an element of the symmetric group. So you have much more options because you have infinite braids that can realize a bijection. And we did a generalization of the symmetric group using braid groups, so braided Thompson groups. So I worked with Julio on that, and then Julio went to work in industry, and he went out of academia, and they have this project about block mapping class groups with Javier Aramayona, who was his advisor. And they said, "Oh, Maria, you want to join this amazing project about block mapping class groups that is a generalization of what you've done in your paper?" And I said, "Yes, of course. I have to learn a lot of things because it's been a while. I haven't been working with mapping class groups." And I joined. And then Rachel, Skipper and Xiaolei Wu, they were doing the same thing. And so we said, okay, we have a team of 5 people doing this thing. And suddenly Julio was out of the picture, and I was with 3 experts in the matter, and I was just looking at them like a cow looking at a train. But I learned a lot of things. I'm not an expert in the matter, but I learned a lot of things. And actually we use cube complexes. So I said, why not trying to explain this for this amazing conference? And because it's used cube complexes, and it's my only paper in which I use cube complexes. So here we go, be gentle with me. And very good. So block mapping class groups.
How do you compose these 2 elements?
Oh, yeah, that's a very good question. So if you have 2 elements, you put one and another, and then you can find a minimum common multiple. So you can, if you have this and you have this, right? So, and the rest of the element and the rest of the element, you can find a minimum common multiple that is 8 in this and 8 in this, and then this can be erased. It's just trying to find the same tree. That adding carrots to both of the trees until you have the same tree. The minimum number that you can add. Yeah, you add them because you have these equivalence relations. You can do that, and you don't have any problem. Okay, very nice. Block mapping class group now. Because this is the only thing I really know. I have a paper, but now I have a paper. So block mapping class groups. As I said, this will be inside the mapping class group of this surface, and I'm going to construct a surface that is isomorphic to this one, but in a way that it is very much alike as trees. Basically, I'm going to construct trees with pair of pants, or 4D with pants for people with many legs. With many legs, right? So basically, I have a surface at torus, but a surface whatever you want, and then I cut a disk in here, and then I add my pair of pants, and I do a tree of pair of pants until the infinity. I go and I go. So this is an infinite type surface. I go, and this is isomorphic to this surface here. We need some definitions. So I call this, so this first piece here, I will call it Y. And this boundary, I will call it B0. And all the others are copies of this, right? All these curves here, I call them I call them suited. And this, in the end, if I select a subsurface, I call them suited boundary components. Okay, so maybe another color. So I will be working, because here I'm not using the infinite tree, but coverings of the Cantor set, so subtrees. Here I'm going to select subsurfaces. So a subsurface is called suited if is a connected surface that is the union of this one, let's call it O, and finitely many blocks. So these are blocks. These are blocks. Okay. So for example, a suited surface is this one. Yeah, it's just selecting a tree. Okay. And this here is what I call suited boundary component. Yeah. You want it to be connected. You want it to be connected. Very good. Now I need an equivalent of these bijections I'm doing here, right? So my bijections here will be homeomorphisms of this super infinite tree. So homeomorphism is block if it is an homomorphism from this surface that I call CD. Sorry, it goes from CD to CD and has the following properties. It exists a suited subsurface. One, this homeomorphism sends Z to something that is also suited. So for example, sends this to this. Second, if you restrict, so I'm doing it well. If you take out the suited surface and you restrict that, it sends blocks to blocks. So it sends something suited to something suited, and then for the rest, a block go to a block to block. That's why it's a block homeomorphism. It doesn't as no block to block. Okay. So the set of block homeomorphisms is a group under composition. It works fine. Suited to suited, suited to suited, blocks to blocks, blocks to blocks. So composition works fine. Everything works fine. So yeah, it's a group under composition. And so for now we have imitated the Higman Thompson groups, and now we want to imitate the symmetric Thompson group. And yes, for now. It fixes, sorry. It fixes this boundary. It fixes this boundary. Yes. It hasn't to be pointwise, but it fixes that. Okay. So now we're going to see what is at H block. And what we do first is that we are going to, we will need a map from the mapping class group of this first block to the others, just to do everything in this first block and then go back, you know. So for every block, we defined a map that goes from this block to the first block Y, and this extends. So it's just, it goes from the block here in the obvious way, in the obvious way. And the important thing is that these boundary components go to this boundary component. And it extends in the obvious way of using notation from the mapping class group of B that fixes this boundary. Let's say B0. We call it B0, sorry. I don't know how to call it. To the map. So here, the one that fixes the one. And once we've done that, we are able to define what is an H block homeomorphism. So we select a subgroup of this mapping class group. We select and we say that F CD block is H block if for every suited boundary with Z defining, because we need a suited surface to be able to define F, right? So we say that one of those is H block if for every suited boundary component of CD minus Z adjacent to A, we have that this composition is exactly H. So basically we are replying these things of labels. Maybe this is a bit bad stated, but what we are doing is in our trees, our equivalence relation said, okay, every time you expand, you have to apply the permutations that the label is saying. Here is exactly the same. Is once you have that, you have labels here, and every time that you want to add a pair of pants, apply the element of H that we have as a label here, right? Is exactly the same, but now we don't have just permutations, we have mapping class groups. So it's you can add it, but you have to do what H says, right? So it's the same. And so we have here also a set of labels that we call H1, Hn, with n is the number of suited boundary components. But it's really the same. It's just you are expanding the thing to mapping class groups. Right. So this is our generalization of symmetric Higman Thompson groups is block mapping class groups. And why I said is a generalization? Well, because there is a kind of obvious suggestion from this to the Higman symmetric Higman Thompson group, right? Because in the same way that we had our 3, 1, and then we have a bijection, and then we had set of labels, and then another 3. Here we have a suited surface, the image of the suited surface, F, that is the block homeomorphism, and then a set of labels, same, and then a set of labels, each one, HN, right? So what is the homeomorphism, the surjection? So the surjection is Z, you can associate a 3 to that. So just send Z to the 3, right? To the obvious 3 that you can have. Fz is also suited, so you also have an obvious 3 that you can have. Then for the then for F, just keep track of the sorry. So yeah, that's this F gives you an obvious bijections between the leaves of the trees, right? It's just, it goes automatically. And then from H to G, what you have to do, because here you have mapping class groups, is just forget everything but how the mapping class groups permute the boundary components. And you have Georgian. So there is an obvious surjection. That's why I said it's a generalization. Very good. Wow, I'm very slow. You are not going to see many proofs. Very nice. Okay, this, everything goes away. So far, so good. So we have seen 1 and 2, and we have to see 3. And because I want you to be reassured, I'm going to now I am able to state this main theorem not poorly stated, and I will be able to prove the corollary. So at least we have that. So the H is going to be the group of H block mapping class groups. So mapping. Okay. So theorem. Now the theorem is the main theorem is BDH is of type Fn if and only if H is. So that's the theorem. That you can choose H to have the finite properties you want. That's the thing. And now I can prove the corollary. So the probability is that the mapping class group of the surface of genus G without a Cantor set contains always a group of type Fn, but not Fn plus 1. And the proof follows from the study of the pure braid group of Starensky. So the corollary, I'm not going to restate it. Proof of the corollary, is just the following. So the mapping class group of my first block, this was my first pair of pants, whatever, my first pair of pants, contain always the pure braid group on the in this case 2 material, in general on the strands. It contains the braid group, it contains the pure braid group. And Ferenczi proved that in this case, the pure braid group contains a subgroup type of type Fn, but not Fn plus. The main why we have that Okay, yes, what I was saying. Okay, very nice. The part is the one that uses cube computation. So I'm going to focus on that. And if I don't have time for the other, we are in Montreal. Okay, so here we use computation and result based mainly in previous papers of Aramayona and a lot of people. I don't have time to name them all, but they are in my heart. Also, Genevois, Lonjou, Uresh, very good friend of mine, and also Rachel and Xiaolei, Skipper and Wu. And what we're going to use is trying to generalize the Stein-Farley complex that is a common tool for studying Thompson's groups. So the Stein complex goes as follows. We have to define our vertices will be classes of equivalence of pairs like that. These are surfaces, suited surfaces, and this is a block homeomorphism, right? And we will say that 2 pairs of that are equivalent if one can take Z1 to Z2 via F1 composed with F, the inverse of F2. And of course, this is the defining surface for this block homomorphism. Okay, so we consider classes. This is an equivalence relations. Everything is very nice. And we will consider classes of pairs like that under this equivalence relation. And the set of all these will be called S. And yes, we will say that this is smaller than this with saying F if, as you can expect, Z1 is contained in Z2. And this gives us a posed structure on these pairs here. So S with this order, partial order, is a poset, and its geometric realization is contractible. I'm not giving many details, but the thing is that we need to work a bit more, and inside this geometric realization, we're only to take some kind of simplices. So we're going to say that if you have a vertex x1 that is Z, F, and another vertex that is Z union something, this is Corley little smaller than that if X is a disjoint union of blocks. So you can, if you have your tree of pair of pans, you can only add one pair of pans in each boundary component. This will be, you cannot do this because then X won't be, it won't be a disjoint union. So it's a finer thing, right? And the Stein complex is the full subcomplex of the geometric realization of S, where the simplices are, so where the simplices are like that. So you have your of dimension n, and you need, so basically you can only add, this is called elementary simplices, because you go one by one. You cannot add a block of simplices just so you go one and then another and then another. So we take those, and this is the Stein complex, and we call it like this. I don't know how to call that, but it's the notation that we use in our article. It's a Greek letter, right? Very good. But we need cube complexes. So good news, we can put a cubical structure on that. So it's so far so good. Yeah, more or less. Okay. So the Stein-Farley cube complex goes as follows. So basically, if you take these sets here, so all the elements that are between X and Y with our finer order, this is a cube. And I will do an example so you won't be bored. So imagine that we have this as a suited surface, so as the defining tree, right? And then we can add disconnected pair of pans. So for example, here X1, here, or B1 if you want, here B2, and here B3, right? So how is this, if this is X and the whole is Y, the whole thing is Y, how is the cube? So the cube is, as you can imagine, I'm very bad at drawing, right? This is a cube. Yes, it's a cube. So if we call this Z, here we have Z, okay, with your define F whatever, then in every this and this we have Z plus B1, Z B2, Z plus B3, and then Z B1, B2. This is the whole thing. This is, so this is X and this is Y, the whole thing. And you know how it works, right? B2, B3. And the one, this is B1, B1, B3, right? So we have a cubical structure in our complex if we consider those as cubes. And 10 less minutes, I'm going to tell you how we, at least the strategy of how we prove this part if. So we use one thing called the Brown criterion that said that you assume that G acts on a n-1 CW complex such that as n-1 connected CW complex such that the stabilizer of every vertex finite, and we have a filtration. We have a filtration. Yes. Such that every element of the filtration is finite modulo the action of G. Then G is of type Fn if and only if this filtration is essentially n1 connected. I don't have much time to explain everything, but basically what we do is to construct a filtration of our complex using heights of vertices. So our vertices are really depending on this type of constructions, right? So we say that an element has height h if h is the number of blocks of the defining surface. So this, for example, the Z has height 2. So what we do is that in our cube complex, we consider the cube that has at most a height h. So inside of our complexes, we go for subcomplexes depending on the height of the elements. And this gives us a filtration for our complex. And then we prove all these things. This is the difficult part. This is the difficult part, proving that it's essentially connected. So when you put one of these inside the other, then you will obtain trivial homotopy groups. So this is basically being connected. But once you prove all of this, you have the if implication. So you have that. Oh yeah. Sorry. So you prove that all these conditions depends on the type of H. So that you have all these conditions if H is of type Fn. And then you have this implication here. And so you have the if part, that if H is of type Fn, then your whole group BDH is of type Fn. I've been very quickly, but that's how the thing goes. For the other part, it's a totally different thing. I have 5 minutes, and it's much quicker. It's much quicker. So for the other part, one staying complex. For the other part, for the if and only if part is totally different strategy. So we want to prove that if H is the contrary, right? If I just prove if H is of type, okay, if, so I want to prove that if this is of type Fn, then H is of type Fn. And this is very quick because we just have to show that H is a quasi-retract of this, because we have this amazing theorem that says, this is Alonso 94, that says that if G and Q are finitely generated groups and Q is a quasi-retraction of G, then if G is of type Fn, so is Q. And the quasi-retraction is super obvious, and you are all going to understand, and I will be finished. So to go from BDH to H, it's super easy, because remember that we can express this as triples. As triples, you have your F, and here you have your set of labels, right? That set you in everywhere. So just take this. Very French, huh? Take this. Takes the fair H1. And this doesn't depend on the equivalence relation, because the first is going to always be H1. Always H1. So just take this. And for the other, it's basically the same. So quasi-retraction, you go and you go in one direction, you go back, and the distance are bounded. No, that is a quasi-retraction. Sorry, I'm being very. I'm stressed. Okay. And for the other, so you take H and you send it to the most obvious thing that you can do. That is basically your set is just your first pair of pants. The same here, your first pair of pants. The identity, and just the labels is H and identity everywhere. It's the most obvious thing that you can do. So if you do this and you go back, the distance are bounded, and then you can apply this theorem, and you have the only if part, and you're done. And that now you can produce your the group that you want inside this family of groups having type Fn, but not Fn plus 1. And that's it. Thank you.
Why is distance bounded?
Okay, yeah, it's a bit it's not trivial. It's not trivial. Like you have to keep track of it, but yeah, it's just a verification. You have to put a distance on it, and
So maybe what is the generating set? Is that easy to describe?
I have the article here. No, it's long. It's long. I mean, yeah, you say. So the thing it's I tricked you, because I need H to be finitely generated to all this to work, but because we are supposing that that BDH is of type Fn, if H has to be of type Fn, because H is basically inside BDH. So it will be a contradiction. So from that you have a set of generators, and yeah, it depends. It's not that easy to describe. No. I don't have the details right now. I'm very nervous. So, but yeah, I can tell you later if you want.
Okay.
Yes. Yeah, I don't remember. But yeah, has many details, but it's not difficult. Go to the article.
One more quick question.
Vivian.
Does the choice of Pence decomposition matter in this case?
Sorry?
Does N depend on your choice of Pence decomposition? Because
Pence decomposition?
for the surface. Okay, maybe it's not a quick question.
No. Tell me what decomposition?
Oh, you chose curves to do the Pence decomposition for your surface, right?
Curves to,
The block mapping class, the block, I'm sorry.
Yeah, the block
The
structure.
way you
yeah,
shape of the class.
yeah, this is not unique. Yes. So,
This depends on the sets of curves that you're choosing.
yes.
So
Yes.
for a different block structure, will we get the same n?
We could. I mean, because you have the equivalence relation. So you have an equivalence relation here, like you had it in trees. So the defining surface is not unique. You can have several. So you can add blocks and blocks and blocks, and this will be also a defining surface. So you have kind of the same equivalence relation that you have in trees. So it depends. It's not different from, it can be the same. It can be the same. There is an equivalence relation on that. So yes, I don't know if that answers your question. Maybe later. Yes. I don't know if I understood the question. Later.
Okay, then let's reconvene at 10 past 12, I would say, and let's thank Maria again.